Yeah, so Rene, as far as I know, he did his PhD at Imperial College in the UK. So Rene can correct me if I'm wrong. Working on the
Correct.
dark side of astronomy, like working on galaxies. He joined Montreal, I believe, in the late 80s, early 90s. I don't know the exact date, working with Daniel Nadeau and René Racine in their starting infrared instrumentation group. He worked on the Monica camera for CFHT, where they did the first trial of exoplanet imaging, I believe in the 1994-ish time frame, if I recall correctly, 95 maybe. Also work on the several workhorse instruments for CFHT, including KIR, which I do remember using. He co-supervised a first wave of students that are now world-renowned astronomers, but I'm extremely biased on that front. He got the big grant from, I think we was part of the big grant, or maybe led the big grant of Montmegantic, where they got a decent amount of money to improve the infrared instrumentation. So one of these was the Trident camera, which we pretty much at the time were starting the field of direct exoplanet imaging, which was my PhD thesis. He's leading the CSA nearest instrument on James Webb, which I'm sure we're going to learn today. He's director of Montmegantic. He started a group identifying young nearby stars. He did weather on brown dwarf with his students. Part of the GDPS, IDPS campaign. These are direct imaging campaign that have led to HR 799 discovery. Part of the GPI instrument, a $30 million instrument now working at the Gemini South, where the 51 Erie B planet was found, the first clear planet with the detection of methane. He's co-PI of the SPIRU and NERPS near-infrared RV instruments that has a very nice synergy with James Webb and potentially also the ELTs in the future. Director of IREX and got many national, international awards and definitely one of the leading astronomers in Canada.
Wow. Well, thank you, Christian.
Got it in a minute.
Okay, well, thank you all for being there. So today I'm going to talk about this topic, which is pretty huge. I realized that I was, setting myself with too much. So in fact, so the first, I'm going to change that slide. So I'm not going to talk very much about detection. I have one slide that will talk about detections of exoplanet with James Webb. And the other thing is that this subject of exoplanet characterization is huge on itself and could be the subject of several teleconf, 1 hour teleconf. And as you'll see, mine is very much concentrated on the hardware side of it. So as Christian mentioned, I spend a good deal of my life, contributing to develop these instruments. And this is, I'm going to give you that pitch today. But of course, I will talk about what we intend to do. So this is my outline. I will give you an introduction to JWST and where we are at the moment, a brief project status. And I will give you some example of exoplanet programs that we'll do with GST with a very near-centric view, which is the Canadian-built instrument. We have a fair amount of GTO time, guaranteed time observations, that we will spend on exoplanet characterization. And finally, a few words about observing with JWST. This big bugger is coming along very, very well. Hopefully, it will be launched late next year. And if you're interested to do observation, well, you should get started. And I'll show you a few slides where how to get started. Okay. So JWST. So this is the one slide description. This is a 6.5 meter infrared telescope. Will be launched in 2018. That's the second Lagrange point. This is the success of Hubble, Spitzer, 4 instruments, very broad wavelength range, 0.6 to 28 micron. Half of its cost, which is about $10 million, that's because it is passively cooled to 40 Kelvin. This is what we need to do infrared astronomy. So if you don't know about Webb, so James Webb was the second NASA administrator that kicked off the Apollo program in the early the 60s. So there you go. That's the project. The main collaboration is NASA, ESA, CSA, and so overall 20 countries. The lead NASA institution is Goddard in Washington, with contributions from GPL. The prime contractor is Northrop Grumman Space Technology. In the early days of JWST, early 2000, the Webb was called NGST, next generation space telescope. For a bit fraction of my life, this was NGST. But when the prime contractor for the telescope was chosen, Northrop Grumman, which was NGST, that was actually a trigger for NASA to change the name. They would not have their big telescope named after their prime contractor. Anyhow, so the operation is the same as Hubble at the in Baltimore, the Space Telescope Science Institute, and the senior project scientist is the Nobel laureate John Matter for the COBE mission. Okay, so just the slide comparing Hubble, JWST, and Spitzer. So you can see for yourself in terms of size, JWST is huge, but the main takeaway is also the wavelength range. JWST is covering the red optical part all the way to 28 micron, and that's a major change. And in the mid-infrared, all we have is basically Spitzer, and you can see the size. I mean, Spitzer is not even as large as one segment. JWST will revolutionize all fields, but the wavelength range that we anticipate to be a major change will be the mid-infrared, because this is where the gain intensity is much large. It's very large. Okay, so this is the JWST orbit, 1.5 million kilometers away. You have to be there in order to be always in the shadow of the sun. Of course, the main disadvantage is that, as you can see here, Hubble is only 500 kilometers away, which you can't service. JWST cannot be serviced. It's a one-way trip. There's 4 instruments. They all have to work. You cannot go there to actually service and change the instrument. There is a hook there to potentially go and grab JWST, but that's not in the plan to actually service JWST. That's a very important point to take away. Okay, so JWST, this is made of essentially 3 things. This is this primary mirror, the telescope, a segmented mirror, the sun shield that protects the telescope from the sun. That's a very important aspect. The science instruments are in the back. There's 4 of them. I'll go through them. And underneath, this is the spacecraft, where the solar panels, where you get the power, and all the communication that to communicate with Earth. So there's always a station on the Earth to in contact with JWST in I believe this is Australia, California, and Spain. Okay, so basically this is a summary of what Webb will do compared to, say, Hubble. Well, this is in the mid-infrared, this is at least 100% more power. Factor of 50 in angular resolution compared to Spitzer at the mid-infrared wavelength. Of course, it's a large telescope. It would, be called a 6-meter fast telescope on the ground, and it's very light, very far away, deployable, and cryogenic. That's half the cost of JWST. That because we're operating at 40 Kelvin. Because there's only one of those, and we cannot service, we have quite a lot of instruments, and they're quite complex. As you see, there's a lot of observing modes, some of them somewhat redundant, and that's what we want for a very complex observatory like JWST, which has a limited lifetime, a minimum lifetime of 5 years, and a maximum of about 11 years. Okay, so there was to do this, there was a number of technological feats that one had to achieve, and I'm not going to go through all of them, but they are listed here. For example, things like application-specific integrated circuit, which are the things that are in your cell phone for controlling the CCD. There are things for granted for ground-based technology, but in space, not. You have to realize that we're operating at 40 Kelvin, so you can't afford kilowatt kind of electronics that used to be driving detectors. So we had to develop these kinds of on-chip electronics, which are now standard. And more importantly, all that stuff had to be space qualified. They have to work in space environment, the radiation environment, and the cold environment. So I'm just going to give you an idea about what was the challenge associated with one of them. So the segmented beryllium primary mirror. This is basically a mass limitation. You have to launch this thing on a rocket, the Ariane 5 French rocket, And so basically we are limited in mass, about 6.5 tons. So obviously the mirror is a major mass budget. So there was a lot of effort to actually develop new mirror technology. There was lots of candidates. And at the end, this was zoomed on beryllium. So just to give you an idea, so this is the 200-inch Palomar telescope. That used to be one of the largest in the world for half a century. So the mass density is about 650 kilograms per square meter. And we know that to go to much bigger telescope, we needed a paradigm shift. That's Jerry Nelson in California that did it with Keck. And they managed to reduce the mass density by a very significant factor of 3 or 4. So the Keck telescopes are, mass of about 200 kilograms per square meter. Now for Webb, now beryllium, as you know, is a very lightweight element. It's also very nice because it has very nice thermal property. So it's a very nice material to use at cryogenic temperature. What you see here is one of the segments, and basically you have to polish these things. They are 1.3 meter across, and the typical aberrations, the typical irregularities on the surface are at the level of 20 nanometers. That's what you need to be diffraction limited around 2 micron. So here you see the backside of it to give you an idea of the scale of this person, and this the actuator system. There's 7 motors that can clock the mirror, tip tilt, do piston, and even the one in the center with these rods that can actually change the radius of curvature. And there's 18 of those, and you can see that about 90%, if not more, of the mass is lightweighted. So and so overall, the net result is that the actual mass density is now down by an order of magnitudes compared to Keck. So that was a major achievement. So here it is. This is done. The actual telescope and the instruments are done, tested, yeah. Okay, very briefly, another big thing is the sun shield membranes. There's 5 of them. So this is one of them here shown. It's an old slide actually. Now all 5 of those are actually built, and they have to be folded. I had a video to show the how this thing unfolds, but I didn't have time to show it. But the point is that on the warm side, it's about 85 Celsius, pretty warm on the spacecraft side, and on the cold side, this is about 40 Kelvin. And so there's a lot of challenge about limiting the conduction between the spacecraft to the telescope. So all that is modeled and also tested. These things were tested at cryogenic temperature to validate the thermal model of these sun shields. Those do not contribute very much to the mass budget. They are very, very lightweight, as you can guess. Okay, so let's talk about the instruments. So this picture is just to show that this is something we cannot do on Webb. This is an astronaut changing one of the instruments. This is what has made Hubble so powerful, right? So that every 5 years it can put new instrument. This will not happen again with JWST. Okay, so there's 4 instruments. So the NIRCam, this is the near-infrared camera, the near-infrared spectrograph, NIRSpec, the near-infrared instrument, MIRI, and the Canadian-built instrument, the near-infrared imager celeste spectrograph, NIRIS. This is our contribution to JWST. There's also, I'll talk very briefly about it, but there's also another instrument on the backside of NIRIS, which is called the fine gather sensor, which is the instrument that keeps the observatory pointed all the time, which is a mission-critical component to the observatory. So this is not a typical kind of instrument suites, even if you compare to Hubble. It's way much more complex. It's a lot of observing modes in both imaging and spectroscopy, coronagraphy, aperture masking interferometry to do high resolution imaging. It's a very, very complex instrument suite. So NIRCam, this is the workhorse near-infrared imaging camera. So there's actually 2 of those. So a long channel and a short and long wavelength channel. So overall, it covers from 0.6 to 5 micron. It is diffraction limited at 2 micron. So that gives you here the actual pixel sampling, 32 milliarcseconds. And it is actually equipped with there's a in one of the mechanisms you can insert a little prism that take an image of the side of the field of view, which allows you to put coronagraphic maps to do coronagraphy for high contrast imaging. But bottom line, NIRCam is a machine to detect very faint galaxies in the early universe. So you see here the focal plane. There's 4 detectors. It's only one. This is one of the short channels. There's 4 of those. So in total, NIRCam has 10 H2RG detectors. A lot of data coming out of NIRCam. NIRSpec. So this is built by Europe, Astrium, and there's various observing mode here. But the main technical challenge here was that the focal plane of NIRSpec, this is a microshutter array where you can do multi-object spectroscopy, and there was a lot of technological development to be done for that. This is contributed by NASA. So the whole instrument the whole optical bench is done in Europe, but the detector are in NASA, and the microshutter array is actually done by NASA as well. So there was a lot of challenge associated with this. The main thing, of course, is that you have to survive launch. This big rocket, that provides the low frequency and high frequency noise, and there was in fact lots of issues associated with this. They're now solved. So here's actually a recent picture just to show that the numbers of actual microshutter that you have here, and it shows you this is the Hurricane Harvey, because the Webb is currently being tested at Johnson Space Center in Houston, and it was tested actually during the Hurricane Harvey, and so the NIRSpec team made this very nice picture with the microshutter array, and it shows the actual defects. So it's not a perfect thing, but still, NIRSpec will be an incredible machine to do multi-object spectroscopy, allowing you to put at least 100 objects at the same time on the focal plane to do spectroscopy. And other modes, which I'll talk very briefly. MIRI, this is the mid-infrared imager. So this is an instrument similar to NIRCam, except that it covers a wavelength range from 5 to 28 microns. And it has also part of its focal plane is to do coronagraphy at those wavelengths. And you can also do single cell spectroscopy, also slitless spectroscopy. There's an integral field unit. This is a device where it allows you to basically take a spectrum for every pixel in your small image. NIRSpec has one too. I'll talk very briefly about that. And so these IFUs are anticipated to be used a lot with James Webb for all kinds of science, exogalactic and also exoplanet. Okay, and finally NIRISS. This is our baby, the near infrared imager and slitless spectrograph, which is basically an instrument very similar to NIRCam. It covers at the same field of view. It goes from 0.9 to 5 microns. And we have basically 3 major modes. One which is designed to do wide field slitless spectroscopy. So it's something very complementary to NIRSpec, but less sensitive because we are slitless. The reason why we put the slit in the spectrograph is that we mask the background. Even though we are in space at L2, there's still some significant background associated with the Zodi light, the zodiacal light in the solar system, and that's the main limitation, the main background photon limitations for JWST. So ideally, you want to put a slit to mask this background, but still, you can do slitless spectroscopy. With the advantage here is that instead of putting 100 objects at the same time, you got 1,000 and even more. So that's a very complementary mode for studying the early universe, and our science team is actually leading that effort. And the one related to exoplanet detection and characterization is this mode here, the SOS mode, the single object slitless spectroscopy, which was actually specifically designed to do exoplanet atmospheric characterization. I don't have time to go to the history of that, but NIRISS had a bumpy ride under the whole JWST story. It was basically conceived in only 5 years ago, or at least not conceived, but the actual implementation occurred between around 2010 and 2011. So way much later compared to the other 3 instruments on board Webb. And because of that, we were able to actually design a mode that was specific for exoplanet. You have to realize that MIRI, NIRCam, and NIRSpec were basically conceived in the early 2000s. So I remind you that the first transgenic exoplanet was discovered in 2000 by David Charbonneau. So we were not even thinking of doing transit spectroscopy. And now, people estimate that Webb could do as much as 10 to even 20% of its time on transit spectroscopy. Okay, so this is our instrument. So you can see on the top, this. You don't see anything because it's all masked up. But the point I want to make here is that this thing only weighs 150 kilograms. It's not that, it's very light. So the guider on the side, on one side, and the NIRIS on the other side. So we basically have two instruments in one box. Okay, so this is the four science instruments together, and it's a very complex 3D puzzle. One very important constraint, as you can see our instrument here, NIRIS, FGS, it's the first one to get in the box. So we are under pressure historically from NASA to deliver first, and we did. We got there. Well, in fact, MIRI got there first, but they had still some issue. But the official working instrument delivered to NASA was FGS. And on the side here, NISBAC. This is huge. This is worth more than $1 billion, that box. Okay, so now the telescope is at the Johnson Space Center in Houston. So that chamber here, chamber A, is the chamber. You can see people here. This is huge. I actually went into that chamber some while ago. It's just very impressive. That chamber was actually used for testing the Apollo, the module, all the hardware that went to the moon, basically. And that chamber has been refurbished for James Webb to become a cryogenic chamber, a cryogenic one. So you can see the actual setup here. So Webb is actually right now in this chamber, and there's some hardware at the top here. This is basically a huge, complex interferometer to measure the surface figure of the primary. Don't worry, there won't be any mistake like Hubble. The regions of curvature is the one we want. And it's complex. There's some flats here to send some back. There's some light source in the middle here to basically check the telescope. So this thing has been operating for almost 3 months. It was the cool down started in mid-July, and we're just at the end of the test campaign, and everything is working fine. I was there a few weeks ago. I had to change my trip because of the Hurricane Harvey. But it's I've been working on this project for 15 years, and I was myself very impressed to see this whole operation, these zillions of tests that are going on. And one thing I have to appreciate, it's not just the hardware we're testing, it's software. The software behind it is so complex. You have to check that everything is working. And it's just very impressive to see the execution of all these tests that have been planned years ahead. And it looks like we're going to finish the test with only a few days late compared to the whole 3 months campaign. So that's very, very impressive. So so far so good. Okay, so this is a picture. Some people worried that would not go in there. It was only 3-inch clearance up there. So you can see just the complexity of getting this thing. And of course, this test you have to do before you cool down, make sure everything is well connected, and lots of details. Okay, so another picture, Johnson, just to appreciate the scale of this huge telescope. Okay, now let's move on to the science and to talk about exoplanet transit. So you're familiar probably with this technique. I think Nick talked about that, and I'm sure we're going to learn more about this by other people within the TEPS. So you're familiar with the concept of transit spectroscopy. So a star, a planet transit, it's a star, and there's two things you can do. You can do the primary eclipse, and you basically that way you're measuring by measuring the depth of the transit, you're measuring the radius of the planet, because we know the radius of the star quite well. Or you can do also secondary eclipse if the planet is close enough, so it radiates at infrared wavelengths, so you get a secondary eclipse when the thing goes back. So the two are very complementary. I'm going to talk more about the primary one, and just to illustrate that, of course, if you got an atmosphere in there, and that atmosphere will not have the same opacity as a function of wavelength. So the radius will appear to change with wavelength, and that's of course the way you can actually infer that the chemical composition. So here's a very simple equation that captures the major physical observable that pertains the transit spectroscopy. So what you're after in transit spectroscopy is this. It's not the main transit depth; it's the variation of the transit depth. So delta F over F, and it's quite easy to demonstrate that that this is given by this equation here. It depends on the equilibrium temperature of the planet, here in unit of the Earth, 250 K. It depends also on the mean molecular weight. So if the atmosphere is made of, say, hydrogen, so mu is 2, so that tends to make the atmosphere puffy, large. On the other hand, if you have a CO2 rich atmosphere, so mu is 44, then that makes the atmosphere much thinner. That makes it much harder to detect. And it turns out, if you do the math, because the actual height of this of the atmosphere is basically the scale height, which is given by the kT over mu g. G is the gravity. And if you put all this together, so the delta F over F depends on the density of the planet. Again, in unit of the Earth, 5.5 grams per square centimeter. And finally, it depends very strongly on the radius of the star. So you see that for an Earth around a solar type star, the signal that you expect to have is at the level of 1 ppm. That's tough. And this is why there's so much push to do that game on low mass stars, because the radius here, instead of being 1, is 0.1, say. So that can boost that signal by a factor of 100. So that's the whole, one of the main motivations for looking to do transit spectroscopy around low mass stars is because it's much easier. Okay, so there's many ways of doing transit spectroscopy with James Webb. So look at the bottom here. So you have here the wavelength range that each instrument can cover. So this is nearest here that covers all the way from the red end of the optical to 2.8 micron. NearCam from 2.5 to 5 micron. NearSpec covers the whole range, but not simultaneously. Nearest is the one that covers the widest wavelength range in one shot. And of course, MIRI as well. So this is a very, very, very powerful capability to do transit spectroscopy. And I'm not going to have time to talk much about integral field spectroscopy. Okay, so a few words about NIRIS. So I'm going to talk to you about transit spectroscopy with NIRIS, but I don't want you to take away that only NIRIS will be used. Of course not. Of course not. There will be many other things. So in a nutshell, FGS NIRIS, this is 2 instruments in a box. So as I mentioned, the fine gather sensor. So this is basically an infrared camera without filters, and its task is just to measure the wobble of the telescope 16 times per second and send an error signal to a fine string mirror buried into the telescope to keep the image very sharp. So we do that with an accuracy of about 4 milliarcsecond. Overall, it's about 5-6 milliarcsecond, or two axes. So to give you an idea, this is the thickness of a human hair at 1 kilometer. That's the level of accuracy we need to achieve to keep the telescope diffraction limited. So this is absolutely crucial. This thing has to work, and it does work very well. One of the very crucial tests that was done at Johnson a few weeks ago was to have the whole things working together, the guider, FGS, the fine string mirror, and the whole software to control that. And it works. On the other side, NIRIS, which I described to you. So this is basically you see here at the bottom the filter wheel. In fact, it's 2 wheel. There's a pupil wheel and a filter wheel. You can see the filters and the various. So this is the element we're going to use for doing single object spectroscopy. This is a GRISM. So NIRIS has 4 observing mode: wide field spectroscopy, which covers that wavelength range. So this is really targeted to do high Z galaxies, and single object select spectroscopy. This is the one I'm going to focus on. So I'm going to go right to the next slide. I've got 2-minute slides, so I won't have time. I want to have some time for questions at the end. So the nearest source mode, as I said, is specifically optimized for transit spectroscopy. It's a broadband coverage from 0.6 to 2.1 micron. And over that wavelength range, we encompasses key features, the key molecules, water, methane, CO, CO2, and even in the blue, metal lines like potassium and sodium ring. So the workhorse instrument on this at the moment, this is with C3 on HST, which covers 1.1 to 1.7 micron. It's actually incredible, the transit science that Hubble has delivered so far, but NIRISS will cover 3 times that wavelength range. So the actual spectral resolution is about 1,000. It varies with wavelength, and that's about an order of magnitude better than with C3. So this is another advantage of NIRISS. And our GRISM was actually built in to look at very bright stars. I'm going to explain very briefly how it works. So this is the GRISM inside the pupil wheel. It's made of 2 parts. The part on the right here, it's made of zinc selenide, which has a directly rule on it. And in front of it, there's a cross-dispersed prism made of zinc sulfide, which allows to do cross-dispersion. So here, this is the spectrum. This is the first order. So 0.7 micron is here. At the top, it's a null figure. It's actually goes all the way to 2.8 micron. And the second order, that goes from about 0.6 to about 1.2 micron. And even the third order is there. You can see that the orders are slightly overlapped at one wavelength. One of the PhD students, Antoine Darvaux-Bernier, is working on actually take care of this contamination that we have between the 2 orders. So and one very key feature of that GRISM, nobody had built that before, is that in front of the first prism, there's a very weak cylindrical lens. This is very exaggerated. And the reason why we do that is to spread light. We do something crazy. We have a telescope which is diffraction limited, and we're actually defocusing the light, but only in one direction, the spatial direction. So you see I'm going to go to the next slide. The width of the trace here is dispersed along the spatial direction, but not along the spectral direction, because we don't want to degrade the spectral resolution. So the PSF you see here was actually measured here in our lab in Montreal, to demonstrate this thing would work, and it does. So in one direction, we're grossly defocusing the telescope to about more than 1 arcsecond. In the other, we are diffraction limited, as you can see here. So that allows you to actually spread the light over many, many, many pixels and observe very bright stars. We anticipate that many of the stars we want to observe are very bright, and our detectors have a limited dynamic range. Beyond a certain point, they saturate. So that was a major drive. Another drive for this design is to you're spreading light over many, many, many pixels, and that mitigate the systematic noise that we're going to have. We're going to try to reach very small, very high signal noise at 5, 10 ppms, ideally with Webb, and to achieve that, we'll have to mitigate what we call the red noise. And spreading light over many pixels is a good idea. Normally, you don't do that when you want to look at faint object, but since here we have very bright objects, we are more limited by the photon noise of the source. We can afford spreading light over many pixels. So that's the trick of the source. But that thing is just only an inch big. So the whole light of the telescope goes through this aperture, this GRISM. We're losing a little bit of light, about 20 to 25%. There was some constraint to do this thing, but it works. So what you're seeing here is an actual simulation of what we see on the detector, and this is the actual real image. CV3 stands for Cryovac 3, the third Cryovac test. We've done three tests of this thing, and we've discovered things that were not working exactly correctly. We managed to fix it, but basically it works. Okay, so a few words about how. So we have a standard mode where we only take a subarray of the detector. The detector is much bigger than what you see here, and the reason we do that is to read the detector faster. There's even a bright mode where we only sample the first order. So that allow us to observe brighter stars. So here you have in the standard mode, we have a saturation limit of about 7, whereas in bright mode, we can push as bright as a 6th magnitude. Okay, one thing that is annoying with slit spectroscopy is that you're taking a spectrum of anything in your field of view. So if you have a crowded region around your star of interest, well, you're going to have contamination. And so this tool here, so what you see here is a tool developed by David Lafrenière at UDM to assess this contamination. Basically, for a given target, this is a TRAPPIST-1 here, and the window that are visible are the ones that are white here. Anything that's ash is not visible, and the position angle is the position angle of the telescope where you can actually observe that. And these colored regions are contamination from other stars. So basically, for example, if you try to observe in this region at this position angle, which translates into a period of the year, well, you would suffer a lot of contamination, whereas this region here is clean. So you have to plan ahead. You have to really have, to check your target whether you're going to have contaminations, and that's part of the planning that you have to do when you want to do this kind of observations with James Webb. Okay, so very quickly, this is the target that we're going to observe. This is the nearest JTO target list. So this is a diagram showing the radius of the planet versus their mass. So all these planets are targets for which we know both the radius and the mass, of course, and the one circle are the one we will observe. So it's anything from hot Jupiters to rocky planets in the habitable zone. So we're going to do it's exploratory project. We anticipate that we're going to observe. We're going to do much more observation after that, and not only us, a lot of other people will want to do that. So it's a very powerful program. This is led by David Lafrenière, and Bjorn Benneke is part of it. Nick Cohen, Ray J is also part of that. So we have about 200 hours worth of time devoted to this thing. Okay, so spectra simulations. So what you see here, one of our prime targets is the first transiting planets, AG29458. This is a hot Jupiter, and this is the WIF C3 observations. That dip here is basically detection of water. So that's the WIF C3 data, and that's the simulated data that we expect to have with NIRISS. So you can appreciate first in terms of the error bars are reduced because we have a much bigger telescope, and the wavelength range, we're covering much more wavelength coverage. So just a few words on the TRAPPIST-1 system that we also is on our list. This is an incredible system. It's a perfect target. It's a dream target because the primary is very small. This is a late M dwarf, and those three planets here, E, F, and G, and maybe D. E, F, and G are smack on the habitable zone. So we will observe F and G, and also D, and other team will observe E. In fact, most of them will be observed with James Webb through JTO observations. So what are we going to detect? Well, of course, it's very speculative at this point. We don't know, but all you can do is to do simulations. I'm showing one of them here, which was actually done by my colleague Bjorn Benneke. So basically, this is a Earth-like atmosphere, which you would put on TRAPPIST-1F. But you make a big assumption. You assume here that the water is well mixed all across also even at very high altitude, and so the blue spectrum is the actual model, and the black point is the simulated observation. You can see that if we have water high up in the atmosphere and we have this kind of atmosphere, we would detect water very clearly with only 4 visits. This is a simulation for 4 visits. I can't remember the number of time. It's got to be something like about 15 hours worth of web time in total. Okay, Someone is trying to call me, cannot answer. Okay, just to show you that this is the HST, so you can appreciate again the power of having a much wider wavelength range, which will be simultaneous, and that is what is unique to NIRISS. Okay, this is a big question that people ask every time leave me alone. Every time I give a public talk, people ask me that question. Of course, we don't know. And if you want my personal opinion, I think it's a long shot. It's a very, very long shot that we will detect a biosignature. So I'm showing you another model. This one is from Victoria Meadows, which has our own model of a modern Earth around a mid-M dwarf, which will be typical, Earth-like planets we're going to find by TEPS, for example. And in this model, where water is somewhat trapped downward in the atmosphere, and it's much more difficult to detect. So the signals are the level of, a few ppms to a few tens of ppm over the whole range, the whole wavelength range of web. Using that specific spectrum, other people have done some simulation of LHS 1140b, which is another Earth-like planet in the habitable zone. This one is around an M5, and the planet is kind of strange because it's got a very, very high density, way too suspiciously high, in fact. But if you take that spectrum here and you try to make a simulations or with the web instrument, this is what you get. So this is a simulation that would use 15 transits, okay, for each band, and none of that cannot be obtained simultaneously. You have to choose a wavelength, and 15 transit in one of those bands translate in 4 years of clock time, because this specific planet is actually, there's only 4 times a year you can observe it. It's not in the continuous viewing zone of GRAC, so there's only 4 times a year you can observe it, and the transit lasts for about an hour, and you observe an hour, half an hour before and after, roughly, and that's it. And you need to accumulate a lot of those visits to build up your signal. So just to give you an idea of the challenge, there's 2 challenges. One is to accumulate enough photons, and this is where NIRISS is well positioned, because this is where the ACD peak, whereas in MIRI, you're running out of photon in this wavelength range. And the main challenge is actually to accumulate enough visits. Okay, so a few words on high contrast imaging. I would have liked to talk to you about coronagraphy. I missed, unfortunately, Christian's presentation on high contrast imaging. I don't know whether he had time to talk about high contrast imaging with web, but there will be a lot of it done. But I want to talk about a very special mode inside NIRISS, which is called aperture masking interferometry. So basically, in our pupil wheel, we have a mask like this, that masking all segments except 7 of those. So it's not a very, in terms of efficiency, it's not very good. But and those segments are chosen such that there's no redundant baseline. If you try to make every single baseline on this mask are unique in terms of position angle and separations. And if you do that, I'm not going to have time to go to the details of it. It allows you to probe very close by to the star at half of lambda over d. So here's one, and so we have some time, some GTO time to look at some exoplanet with that. So the contrast that you get is relatively modest compared to classical coronagraphy, but you can get much closer. So here's a contrast limit that we expect from the IME mode with NIRISS. And you see it goes all the way to 0.4 micron. But the inner wanking angle of the near-cam chronograph is off scale here. It's 0.6. So this is very, very complementary to the near-cam. So this specific target, this is AG95086, which was discovered by Julien Rameau in 2013 to have an exoplanet run at a 4 Jupiter mass object. And this star has a disk, and it is suspected to have other planets inward, maybe from 2 to 4. And the GPI observations are actually ruling out another planet in there, but there may be others inward. And if there's a 5 Jupiter mass object within 0.1 to 0.3 arcsecond of this thing, NRM will detect it with NIRISS. So it's going to be a very exciting target to look. And we're going to look also at other treasures and disks stars, which I won't have time to talk about. But just to tell you that it's quite likely that JWST will have new detections of new planet, possibly using that technique. Okay, I want to say a word because I know there's a lot of people in the room interested by planetary science. So this is exciting stuff that Webb will do. This is part of the JTO targets of Heidi Hamel, not Hammer, sorry, sorry, Abel, and to observe Europa and Enceladus with JWST using the NIRSpec IFU. I will explain briefly what is an IFU, but basically the IFU NIRSpec allows you to take a spectrum for every pixel in this image. So this is a picture of Europa with the plumes that have been detected by HST, and on the right here, this is an actual simulated spectrum that obtained with NIRSpec, and you can see that all these molecules could actually be detected remotely on Europa and also Enceladus. So it's going to be exciting science being done. One challenge of these things is that they're moving around, right? And so we had to design the guider, our instrument, to actually do that, to keep track of these moving targets, which is not trivial. And it was not part of the main capability of the telescope. Even back in the late 2000, the science working group had to work to get these things implemented, and it's now in the baseline. Okay, so just to finish, a few words about integral field spectroscopy, just to explain the actual how it works. So you've got a scene here, a galaxy, and you've got a device like this thing on the right, which is this micro mirrors that slice the image and configure them into a long slit, and then you enter that into your favorite spectrograph, and then you disperse. And so each subslit is actually dispersed, and from that you can reconstruct a data cube. So for every pixel, I have a spectrum. So this is extremely powerful. Now, in the context of doing exoplanet characterization, things that you can see aside a bright star, which we have a good example of that already in the high contrast imaging business, the IFU will be. I anticipate that IFU will be used a lot to do exoplanet characterizations, both with NIRSpec and MIRI. So MIRI and NIRSpec have IFUs like this. Okay, so I want to finish to tell you about, if you want to learn more about JWST and how to prepare a proposal, well, there's basically two things you need to go to Google. First of all is JWST Pocket Guide and JWST User Documentation, and I will bring you to everything you need to do this. And also, we will organize a series of webinars this fall, starting in November. We will advertise them. We'll have a series of about 5 or 6 webinars organized by our team to present you these various observing mode and help you out to prepare a proposal. And we're there to help you. So so on that, I guess I'll stop. And just to this is actually what will be pronounced, because we're going to be in the French Guiana in 2018. It's actually 3, 2, 1, top, and the thing will go. So I'll stop here and leave the actual latest deployment, which I call the 14 Days of Terror, and I can take your question if you have any.
All right, so are there questions for Renee? Oh, okay, I guess I'll start, I'll jump right in. So I was